Well, hello friends. Today we're going to work a little bit on disk performance because we have this problem in Serenity that writing stuff to the file system is very slow. And I think we can do some improvements quite easily. So we have this disk benchmark thing. That backslash was me accidentally typing. And every dot here represents, first we write a file of this size, and then we read the whole file back in. And every dot is one successful write-read cycle. And basically, the test runs for a set amount of time, and you can see here that we completed 57 runs in that time, and the time is like approximately 10 seconds, right? So 57 runs in 10 seconds is our current write performance here on this. And then, I mean, it goes through a set of variations of like different file sizes, different block sizes, stuff like that. But let's just see if we can do some stuff to make this go significantly faster. So I know that on the ext2 file system, when we write something out, then I guess I know that okay. Let me not make assumptions. Let's just run with debug, and we'll see what it's doing when we're running the test. Okay, so the test is going. I'm getting dots and getting lots of spam. Okay, so we can see here that there is a lot of I guess this is removing a file because we are changing the block allocation state from 1 to 0. So I think that means that we are indexing group blocks and blah 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 blah. Yeah, right. We are freeing blocks. So this is the deleting the temporary file part of the cycle, which is also counted towards the performance. But anyway, we are doing block allocation, block deallocation, and basically for every single block of these files, we call set block allocation state. So let's take a look at that. Okay, so what this function does is basically it finds the bitmap for the block group, and then it will flip the bit for an individual block to 1 or 0 depending on this state variable here. So this looks pretty inefficient, right? Because we can see here, first we compute like the where the bit is exactly inside of the bitmap block, and then we read the bitmap block from disk, and then we change the bit in the bitmap and then write out the whole bitmap block to disk. So that's pretty inefficient right here, because we're like reading a whole block from disk, changing one bit, and then writing it back to disk. And then we also have to update the super block of the disk, which is like the main metadata block that's like at the start of the disk. And the super block contains all of the like the top level information about the file system. So this is the definition of that, or declaration. And it has all these little things like how many inodes, how many blocks, how many free inodes and free blocks and stuff. And in fact, the number of free blocks is what we have to update here. And then after we change the number of free blocks, then we write out the super block to disk again. And then we have to do the same for the block group descriptors. So we just an ext2 file system is divided into block groups, and block groups are described by these group descriptors, which look like this. They're like, I don't know, how big is this? 32-byte data structure that there's one for each block group, and there's so and so many blocks per block group. So basically, whenever we allocate or deallocate a block, we have to update the number of free blocks in the super block and in the block group descriptor for the block that, for the group descriptor for the block group that the block belongs to. So essentially, we have to update two counters, super block counter and block group counter, and then in addition to the bitmap itself. So that's a lot of churn for all of these. So every time we change the allocation state of a block, we have to do all this disk traffic. So let's do a bit less of that. I guess we can start with superblock, making that lazy. So currently we store the superblock. We have a byte buffer where we cache the superblock, and we also have a byte buffer where we cache all the group descriptors. So these things are already cached. And I'm pretty sure we always use the cache. We never actually fetch from disk. We just write out to disk whenever they change. So it should be a prime candidate for laziness. I think, in fact, we could just do something like, instead of saying write superblock, we could just say m superblock. M superblock dirty, true. And in fact, we could probably just do the same here. Instead of flushing the block descriptors to disk, because that's what this one will do. We'll just flush them to disk immediately. So we can just say block group descriptors dirty. And let's see, where else do we do write superblock? Let's find everyone who does that. Okay, here's another one. This inode allocation. Inode allocation and block allocation is very, very similar. In fact, we could probably share some code between those guys. Is that the same thing I called it in the other place? Yes. Okay. Write superblock. Okay, and flush block group descriptor table. We're still doing it in a few places. Well, what if we just block group descriptors dirty true? So we never explicitly flush these. We just say that they're dirty. And of course, we're going to need to remember this. So this would be false by default. Okay, and then so we have this thing that on startup we create a sync daemon, which every 1 second it will wake up and flush anything unwritten to disk. And maybe it should be less often, I don't know, but that's currently how it works. And the implementation is just that it's just called sync, which in turn calls VFS sync, which apparently calls FS sync. And then for each file system, we call flush write, which is virtual, but oh, it's overridden by diskback file system. So ext2fs, the ext2 file system, it inherits from diskback file system. And diskback file system provides a block level cache. So we're not actually writing to disk. When we write to disk, we actually write to the disk cache, and then the disk cache will be flushed to disk. But this is already a pretty heavy operation, because if you're only changing like 1 bit or 32 bits, then it's kind of silly to read and write like a whole block for that. A block in this case, I guess, is what is the block size? Dump b2fs disk image less block size is 1 kilobyte. So we're reading it and writing 1 kilobyte in order to alter 1 bit. So that's pretty silly. Or 32 bits. So I think this will probably be significantly faster already with these changes. But of course we have to actually flush the writes. So I guess we can just override flush writes in ext2 file system. So I'll just put that here. Virtual void flush writes. And here, gotta make sure to call this one when we're finished. Okay, and then if m superblock dirty, write superblock, I guess superblock. Okay, and if m block group descriptors 30 flush. Okay, that's actually really straightforward. Let's try it. Oh, we got debugging still turned on. Let's turn that off. Disk benchmark. Permission denied. Ooh. Wait, did I forget to sync last time or something? I don't feel like I did. Okay, here we go. It definitely looks faster than last time, but I'm not sure how much. Oh yeah, right, so what was it last time? 56 runs. So it's a pretty solid improvement. 6.6 times more runs in 10 seconds. I should have written down what the write BPS was. I think it was something like 2 megs per second, and now we're up to 8 megs per second. Of course, this is not so much of a disk benchmark as it is really a file system benchmark, because what we're doing here is file system optimizations, and the thing that it's testing is file system performance. But the name disk benchmark is okay. So actually, let's see that we didn't break something. Nope, file system looks okay. So let's look at this patch, because there's a bunch of cleanup we could do here. I don't love the way it looks, but it's a good start, I think. So we're just remembering if these metadata collections are dirty, essentially, and then when we get told to flush writes by the sync call, then we write these out if needed. Okay, so ext2fs. Make flush superblocks block and block group descriptors lazily. And keep dirty bits for these and override flush writes so that we can defer writing these out to disk until syncd until we have to. Well, it's not really about the deferral, it's about the coalescing of writes. That's what makes this so powerful, right? Because so we can coalesce writes. Because by coalesce, I mean now that we are just mutating the cached block. So essentially, we have these two here, right? This is the super block, and this is the block group descriptor table. And now when we want to change something about the super block, we're just changing our cached copy of it instead of reading it from disk, or instead of like modifying our cache copy and then writing that out to disk every time. Like we now coalesce all those writes so that you might have had like 100 writes before, and now you get only one every 1 second when it does the thing. Anyways, you know what I mean. Looks like a 5 to 6x performance, write performance bump on the disk benchmark. Let's be conservative and say 5x. It's pretty good. But this makes me wonder, like, why is this even in a byte buffer? Like, because byte buffer is a heap allocation, and we probably only ever allocate these on startup, more or less. Yeah. The first time that we call superblock, we'll read the superblock, and then we never ever read the superblock again. Because this is the only thing that calls it. So instead of having this be a byte buffer, we could also just have it be a 1 kilobyte 1 kilobyte raw byte buffer instead of a heap allocated byte buffer. So it could be, or how big is this thing? This thing is the right size. It's 1 kilobyte. So we could actually even have it be one of these. And we could read right into it. Okay, let's do that. Let's say ext2 super block. I'll just do that. And super block. And who's the first one to call this? I guess in initialize. First thing we do in initialize is call superblock so that we read the superblock, right? So instead here we can just do something like, I mean, we can call read superblock, I guess. And then we're using it a bit. I mean, I guess this is okay, or no, let's call read separately, okay. And then what this will do is that we will just read it directly into superblock. Oh, it's const. All right, well, whatever. This one, though, it's a bit different because we don't know how many of these we have up front. It might be different, so we can't, like if it's a big disk, it will have more block groups, so we don't know. But this one is static sized, so let's make it static sized. Superblock. And then we want to go halfway into the superblock. So, wait. This thing has a read block and read blocks, and we just want to read 2 blocks here. Because this is a bit confusing, but the device has his idea of block size, and the device is like a disk device, and that's normally 512 byte sectors. But then the file system has its own idea of block size, which is 1 kilobyte in this case. So to read the superblock from a device that has 512 byte blocks, we end up having to read twice, but this is probably silly when we can just do read blocks. 2, 1, and the pointer. Can we do that? And it's not const. Wait, what? I was able to call this, but not this. Oh, this one is this weird. Okay, I don't know why it's like that, but let's constcast our way out of it for now. Disk device. Okay. So we can get rid of the buffer. Can get rid of this. And don't have to return anything. And we can just do this in initialize. So initialize. Okay, so we don't need the lock because we're initializing. This is only done once on file system initialization, so there's no need to lock it because it's still being constructed more or less. Okay, and then superblock. This thing becomes very simple because it can just return m superblock. No need for a weird casting helper like this thing right here. M superblock. And then write superblock. This is also like, why do you have to say that you want to write out the superblock? Can't you just say flush superblock? And then where do we have that? Write superblock right here. We'll just rename it to flush superblock. That one disappeared. Okay, write super becomes flush superblock. And then let's do this in one go. So we'll just say m superblock. Const u8. Okay, because we don't need to refresh some superblock cache. So I don't know why that was there. We can just get rid of that. Okay. Now this is starting to look a bit tidy. I mean, not the whole thing, but this tiny little slice of it. Okay, mcached. Where's mcached superblock used? Oh, okay. So when we're mutating the superblock, then we were doing that. Well, we can just do. Why don't we have a mutable superblock? Or actually, why do we even need a separate thing? We already have m superblock. So we can just use this everywhere. Oops. This code is not super tidy looking, but but it's okay. We can do better, but we don't have to fix everything right now. Okay, let's try this out. I just want to see that things still work. Disk benchmark. Look at it go. It's pretty nice. Yep. Okay, and we didn't break anything. And let's just do a general insanity test. Oops. Yep, stuff still starts up. No big deal. Snake still works. Okay, well, that's good. So what did we do here? We changed the storage of the superblock in the ext2 file system from being a heap allocated buffer to a member, simple member, and then instead of making it lazily loaded, we just load it up front once in file system initialization, because that's effectively what was happening anyway, because we were always calling superblock the first thing we did. So the lazy loading mechanism was completely pointless. And then we also use device read blocks and write blocks so that we don't have to do two I/O calls. We can just do one single I/O call, which is actually nice because it means, I mean, when it comes to reading, it's not terribly important because we only read once, right? But every time we flush it in one disk operation instead of two. So it's not going to hurt us. Okay, so let's commit. Oh, my C key is sometimes not registering anymore. That's a bit silly. Come on, C. Clean up or tidy up superblock code related to ext2 superblock. Super cached superblock as an ext2 superblock member instead of an a byte buffer and using a casting. Helper everywhere. This patch also combines reading, writing the superblock into a single disk device operation instead of two. Yeah, that's pretty good. But in block allocation, though, we still do that silliness where we read out the whole block bitmap just to change one bit. And we can definitely improve that as well. So that's here. We figure out which block the bitmap, the relevant bitmap is for this block allocation change. And we read out the whole block and then change the one bit down here and then write out the whole block. Oh, it's so gross. What if instead we could have a cache of block bitmaps or cache of bitmaps with a dirty bit in the ext2fs. And then when we flush writes, we'll flush out those things. I think that could work, because then we don't read the thing every time. So here, instead of read block, we'll do something like get bitmap. Okay, so how would this work? Get block bitmap for, I mean, we want it for the block index, actually, so maybe all of this stuff here can also be moved. So we want to get the block bitmap, and then we would get rid of this stuff. Or at least we would move that stuff. So let's write this thing out at the same time, actually. Bitmap. Block index. Okay. And what that thing is going to do is all of this stuff right here. So So we'll figure out where the bitmap is. We don't need the bit index, I guess. I mean, it's not going to hurt us, but we don't need it. So we'll put that down here. And we don't need to create the block, but we'll do it up here. And oh, wait, hold on. I have two editors. Why am I not using both? Okay, so we get the bitmap, we compute the bit index, then we print out that we're changing something. Oh, index and group, we need that in both. Crap, all right. I guess I can put these up here. It's okay. And then we don't want to write block here. This is something that we'll do later. So when we give you a bitmap, it needs to know the block index for that bitmap. So what we're going to cache here is, let's see. Cached bitmap. I guess we can store a K buffer for the block, I'm thinking. Or let's just use a byte buffer for now, just out of, for simplicity, but wait, K buffer can't be null, right? Yeah. It needs to know the block index, bitmap block index, and it needs to have a dirty bit. Okay, so then we can say that vector own footer cached bitmap something like that. And then when you ask for a block bitmap, we compute, this is the block bitmap, right. So here, we have to see if we have this already. So cached bitmap and cached bitmaps. If cached bitmap dot bitmap block index equal to, if it's the same, that one that we're looking for, then we will return cached bitmap I guess we'll return one of these, like a wrapping bitmap. Cached bitmap buffer data. Oh, right. Let's see if we're doing this right. It's okay for this thing to be a wrapping bitmap, right? Yeah, right. Because you can copy this thing or you can move it. Okay. And it will still refer to the data in this buffer. Okay, so there we go. Otherwise, we didn't find it. So then we gotta fetch it. So we don't need the indexing group here. Let's get rid of all this debug logging. It's just confusing me anyway. So we didn't have it cached. Then we'll read it, and we will say cached mcached bitmaps append. Damn it, I forget what's in the cached bitmap already. These guys, right? Just a cheat sheet. Okay, so the bitmap block index and the dirty bit and the buffer. So I guess block. And then we will just return it. Oh, it's an own pair, right? Then we'll have a constructor for this, so it'll just be block index like buffer bitmap block index and the dirty bit will always start out as false. I think that's okay. And I guess maybe we should give you the cache bitmap actually. Yeah, I think that makes more sense because then you can modify the dirty bit if you want. Okay. We'll have one for inode bitmap as well. These things don't need names because they're redundant. Okay, and then we'll just return the cached bitmap like this. And we can be friendly here and make a function. Return something like that. That's probably, I don't know how big that is. Yeah, it's an unsigned. Okay, well, let's have a U32 for it. I think that's okay. Okay. So now the way we would use this is cached bitmap bitmap get. It's nicer. Well, no, this is okay, I think. for now. Where does the group index come from? I realize this might be a bit hard to follow along here. It's kind of tricksy to add caching to something existing. But let's see. So now we want to do cache bitmap, bitmap set. And yeah, we have to pass the blocks per group every time we instantiate a bitmap. It's not ideal, but and here we just set dirty true. This is going to be the magic thing that actually causes it to get flushed later instead. Okay, and then let's see. So where we do flush writes, we'll say for auto cached bitmap. Then write block. Bitmap block index and cache bitmap buffer data and clear the dirty bit. Okay. I guess we can print something out here. Flushed. I'm very interested to see how this will work. Okay, we have some stuff to fix first. This thing doesn't exist. Okay. I guess we moved it up here. So what did it say? Group descriptor for group index, right? Well, let's just move forward here and see what we can achieve. Make cached bitmap. We have to move the block. Will this remotely work? I have to sync. Oh, okay, so things went wrong. Set block allocation state, we are asserting on 1246. Okay, we shouldn't be here. So we're trying to set the state of a block to the same state it already had. Let's add some debug output so we can see what's going wrong. Okay. So we're trying to set the allocation state of this thing from 1 to 1. Get block bitmap. Oh, it's a little warm here. Get block bitmap. So if we're trying to set it to the same thing it's already set to, where did we set it the first time? Okay, so we set it to 1 up here, but then later on, I guess we allocate the same block again. So it would seem like when we allocate a new block, we're getting a block that's already allocated, which probably means that we didn't write the allocation statement to the right place. Block allocation state is called by resize. Okay. Well, it doesn't matter who calls it. It's just doing something differently than before, right? Oh, is this thing making a copy? I guess this is making a copy. We don't want that. And we gotta build a new file system. Because, you know, when you're working on a file system code, you're constantly corrupting your file system, and you gotta make sure you rebuild it. Okay, well, we're failing again, same place. But why? Flushed bitmap block. Well, that's at least we're doing those. Okay, let's just enable these. And we can say what is it called? I need this thing. Let me put it up top where I can see it. Oh, well, that wasn't right. Wait, why did that go so wrong? Okay, I don't know what happened there. So we're doing 1, 1 and 1, 4, 7, 4, 5, 7. We're doing the same thing up here. So here we're setting it to 1, but I'm guessing that it does not. Oh, wait, hold on. Get block alloc, is there such a thing? Do we have some other code that looks in these? Allocate block. Right, so the code that allocates blocks, it doesn't care about our cache. So we have to fix that. Okay, well that makes sense. Because yeah, you can see here it just reads the block without thinking too much. So then we'll do auto cached bitmap is get block bitmap for I mean, maybe we should make get block bitmap take a group index instead, now that I think about it. So we have a group index. Or we could even do this, actually. Okay, let's do that. And then we can get rid of this code. This needs to be amp. And for this, we can just say cached bitmap dot buffer. Okay. Then we should change this. Bitmap block index. That simplifies this quite a bit. Because then we don't have to do any computation in here of which block index to use for the bitmap. I'll just make it clear, yeah. Okay, so it's getting a little bit better. I mean, abstraction-wise, it's getting a little bit better. Now, okay, so at least we are progressing, we're not crashing immediately, so let's turn this off and see how we actually do. Wow, look at it go. It's up quite much from 350 whatever we had before. So it's almost another 5x. I'm bad at math. Let's say 3x. Approximation is tricky. Right, so okay, so did that corrupt the file system? It didn't. Basic stuff seems to work. Can we build a program? Well, we need to fix it first, but it totally works. All right, all right. That's so awesome. Okay, so let's see. Flushed bitmap block. I guess we don't need that to be always coming out, you know. What else do we have? I think that turned out pretty good. Cached bitmap. Yeah. It's pretty sweet. Okay. So let's commit this and then do it for inode bitmaps as well, because there's both block bitmaps and inode bitmaps. cache block bitmaps. Instead of always reading, writing disk. Add a simple cache to ext2fs where we keep bitmaps, block inode block bitmaps, along with a dirty bit. This allows us to coalesce bitmap flushes, giving us a nice 3x improvement in disk benchmark write speeds. All right, I mean, I know that I'm not being very rigorous with like the performance improvement numbers, but it's just for scale, you know, just so you get an idea. Okay, so right, the inode bitmaps, because we have inode allocation state as well, and this thing can also just do what we did for set block allocation state. So dum. Okay. Oh, I gotta set dirty here. Is it that simple? Wouldn't that be nice? Allocate inode. Yeah, let's not forget about this time. So this is where we grab those. So we'll just do auto cached bitmap is get inode bitmap. But really this could just be get bitmap block actually. Okay, and get block bitmap. And then let's rename it to get bitmap block. Yeah. I don't know. This will probably not do nearly as much for the speed because when we're doing the benchmark, oh yeah, we just fall apart. Great. So what did we mess up? I guess allocating the inode fails somehow. We fail in create because we have some kind of error. All right. Allocate inode. I'm sure I made it fail. Get bitmap block. Wait, why would this fail? Okay, now I wish I hadn't done the two changes at the same time. So let's do them over. So first off, let's just change this thing, rename it to get bitmap block. Or hold on. I forget what I'm trying to do. Patch. Let me reapply the patch and fix this up. Okay, hold on. Get block bitmap. Okay, now we're gonna fix this. Everything's still good, obviously, because it's just a name change. Okay. Bitmaps as well, so let's rename it. Okay, now I can copy in my changed file. And we have only the relevant changes. Okay, that was a really roundabout way of doing that, so I don't know why I had to do it that way. There was no need. Anyway. So we're using blocks per group. That doesn't seem right. ext2 file system. Allocate inode. I bet that's the bug. I was just not changing that. So instead of passing blocks per group, where the hell is that even? Set inode allocation state. Oh. And what were we doing previously? Inodes per group. See, that makes a lot more sense. Inodes per group. So that's stupid that you have to pass that in. But I guess it's not the end of the world. Oops, this is still not right. So what's different? No, okay, I just wanted to believe. Okay. So previously we were fetching this block. Is there some other place where we're not respecting this? Yes, here, get inode allocation state. So that's also used. Okay, so we got to make that one work. Get bitmap block. Inode bitmap. And then return cached bitmap.bitmap. Inodes per group dot get int index. Get bitmap block. Oh, well, this thing should probably be. Okay, we're gonna const cast our way out of this now. But I'm not exactly sure. Wait. What was I trying to do here? This. I mean, we should have a version of this maybe that gives you a const cached bitmap back for read-only access. I think that would be okay. Okay, so now even the inode bitmaps are also cached, which means that every time we create a new inode, or look for an existing one, then bitmap lookups are faster. Bitmap lookups are faster, hopefully, but also writing to the bitmap is definitely faster. Look at him go. All right. And just to make sure that everything's still, ooh, things are looking wrong. I wonder if that's caused by this. Let's give it one more shot. That one's very suspicious. So we're good, but maybe it gets corrupted by some other bug, who knows. But I think the general mechanism here is working nicely. I guess we can see if it runs to the end. These write speeds are looking very nice. Remember the first time I ran this program, it was in the kilobytes per second. And now we are seeing megabytes per second, which is nice. Or nicer. I think it's going to go up to 5 megabyte size file. In fact, I don't know if I have space for that. Oh, interesting. You can see it pausing there, I guess, when it's flushing to disk. Flushing suddenly gets kind of heavy. Well, there's all kinds of things here that need fixing, obviously. Let's just, oh, there we died, and things go wrong, and what the heck? What just happened? Let's see. Let's commit this first of all. Use cached bitmap blocks for inode bitmaps. Use bitmap block caching for inode bitmaps as well. Nothing showed up on disk benchmark for this change, but it seems sensible regardless. It is. It's the same mechanism here. Okay, so it's definitely a little bit of weirdness going on when we get to the bigger sizes. I don't know what's causing that. I don't know if it's my hunch says that it's something unrelated to this because it started triple faulting, which is very suspicious. Or actually, no, that was not triple faulting, but it started going in a reboot loop, and I don't know why. So it seems a bit strange. But anyways, I don't really have much more time right now, so I think we're going to end it here for today. Oh, we have to do this, but we've been able to squeeze out some pretty good performance improvements here. So I hope you've seen something interesting. And this is definitely something that's going to need more work, both in terms of bug fixing, performance fixing, and so on, but things are getting better, clearly, a little bit at a time. So thank you for stopping by and checking this out, and I'll see you next time.